Hello. In this video, we're going to look at the primary trigonometric ratios. But first, let's review some things about right triangles. So I have a right triangle here, and what I'm going to do is I'm going to represent each vertex or point of the right triangle with a capital letter. So let's call this point A, point B up here, and point C for the right angle. Now what I'm going to do is I'm going to use the corresponding lowercase letter to represent the side opposite each vertex. So this vertical side, for example, will be lowercase a because it is on the opposite side of the triangle from vertex A. The horizontal side will be a lowercase b because it is opposite to vertex B. And the hypotenuse, which is the longest side that is opposite to the right angle, will be represented with a lowercase c. So hypotenuse is the longest side, and the two shorter sides are called the legs of the right triangle. And we know something pretty important about right triangles, and that is that in a right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. This is known often as the Pythagorean theorem, a squared plus b squared equals c squared. This is true in any right triangle. And in fact, if it is true of a triangle, then we know that that triangle is a right triangle. Now, let's consider a series of similar right triangles. So I have a bunch of right triangles here. I'm still going to call this vertex on the left-hand side vertex A. But I actually have a bunch of different other angles. So the right angles are down on the bottom line and up top. So I'm going to call these points B1, B2, B3, and C1, C2, C3. Now, what I know is that for all three of these triangles, so the smallest triangle, which involves A, B1, and C1, and then we've got A, B2, C2, and A, B3, C3 would be the largest triangle, all of them share angle A. So for all of them, angle A is equal to angle A. Obviously, an angle is equal to itself. They all also have a right angle at C, C1, C2, and C3. So because two of the three angles are the same, the third angle must also be the same for each of them. So the angle at B must be the same for all three of these triangles. So that's based on the fact that we know that all the angles in the triangle have to add up to 180. So if two of them are the same, the third has to be the same so that the sum will be the same. Now, because all three angles in these triangles are equal, that means that these are similar triangles. So triangle A, B1, C1 is similar to triangle A, B2, C2, which is similar to triangle A, B3, C3. Similar meaning that they are the same shape, but not the same size. We know they're the same shape because all the angles are the same. Now, they don't have the same size, but what we do know is that their side lengths are proportional. So that is going to be important. What I'm going to do is I'm going to name these sides as I would name them, where I use the letter opposite to the side, but I'm using a subscript for each of these triangles. So A1, A2, A3. I've got B1 as this shorter side. B2 will be this entire length right here. And B3, I haven't left myself much room, but B3 right here will be that whole length. And then as well for the hypotenuse, I've got C1, I've got C2, and we've got C3 for the full length. Now, because these triangles are similar, we have proportions. So for example, the ratio of A1 to B1 has to be the same as the ratio of A2 to B2, which has to be the same as the ratio of A3 to B3. Now, we've already seen this as slope. The hypotenuse is all one line, so the slope between A and B1 and A and B2 and A and B3 has to be constant, and that slope would be the vertical change, A1, over the horizontal change, B1, or A2 over B2, or A3 over B3. So this already is something that we know based on slope, but it is also a property that we can say of angle A. So angle A will always have this ratio when we draw an angle this size from, say, a horizontal line. So if I draw a diagonal line sloped at a particular slope, that slope will be constant. So we actually call this the tangent of A. So the tangent of angle A is the ratio of the opposite side to A divided by the adjacent leg. So we're ignoring the hypotenuse. So the opposite leg and the adjacent leg to A will be in a ratio of A1 to B1, or we call that the tangent. We do that so that even if I rotate that right triangle a little bit, so if I rotate it so it's like this, so that these lines A and B are no longer vertical and horizontal, but they are still the opposite and adjacent sides to A, then I can still have that similar ratio, even if I can't properly call it a slope. So that is the tangent of A. But actually, any of the ratios of sides in this triangle will also be constant. So I used A1 to B1 to start because we're already familiar with the concept of slope, but I could have said that the ratio of A1 to C1 and A2 to C2 and A3 to C3 are also the same. And this is where I'm looking at the opposite side, the opposite leg, and dividing it by the hypotenuse. So this is the opposite over the hypotenuse. We call that the sine ratio of A. So for any angle A, that sine ratio, no matter what size right triangle I draw, if I have an angle, a particular angle, so a 20-degree angle, for example, and I draw a triangle, a right triangle that has a 20-degree angle, and then I measure the opposite side and divide it by the hypotenuse, I will always get the same ratio, no matter what, no matter how big I've drawn that triangle. And if you're curious as to what that ratio would be for 20 degrees, for example, it would be about 0.91. How do I know that? Well, I know that because I can plug that into my calculator. I can actually type what is the sine of 20, or I could know it by actually just drawing a right triangle using a 20-degree angle and measuring the opposite side and the hypotenuse and dividing them. So just to reiterate back here with tangent, it was the opposite divided by the adjacent. Adjacent just meaning beside or touching. So the adjacent leg is the leg that is touching A, and the opposite leg is the leg that is on the opposite side of the triangle. There's one more ratio we could have looked at, and that would have been B1 to C1, or B2 to C2, or B3 to C3, and those would also be equal because these are similar triangles. So in other words, if I take the ratio of the adjacent side divided by the hypotenuse, and we call this the cosine, which we abbreviate COS, the cosine of A. And again, these are going to be constant no matter what. So if I draw any right triangle, so let's say, for example, I have this right triangle, and I'm going to call this DEF, for example, which means that my hypotenuse is going to be a lower letter f, and then I will have this vertical side with a lowercase d and the horizontal side with a lowercase e. Now let's say these angles are, I don't know, let's go 15 degrees, and if I have 15 degrees and 90 degrees, then this has to be 75 degrees so that they all add up to 180. So what I know then is that the sine of an angle, let's start with tangent actually. So the tangent of an angle, so let's say for example the tangent of 75 degrees, is the opposite side divided by the adjacent side. So opposite to the 75 degrees is D, divided by the adjacent side, which is E. If I change the angle I'm looking at, so instead of thinking what is the tangent of 75 degrees, I now have the tangent of 15 degrees. Well, 15 degrees has an opposite side of E, and the adjacent side would then be D. The sine of 75 degrees, well, that would be its opposite side, D, divided by the hypotenuse. Or the sine of 15 degrees, well, in this case, the opposite side would be E, divided by the hypotenuse. And the cosine of 75 degrees, well, that's the adjacent side, which is E, because that is the side that is touching the 75, divided by the hypotenuse. But the cosine of 15 degrees is actually going to be D divided by F. So the hypotenuse is always the hypotenuse, but which side we consider to be opposite or adjacent depends on which angle we're talking about. And in my calculator, I could actually figure out what these things are, and I can then use that later on to solve and figure out what side lengths and triangles are. But I could plug into a calculator what is the tangent of 75, And it would tell me that the tangent of 75, I actually was in the wrong mode in my calculator earlier when I told you that the sine of 20 was 0.9. It is not. The sine of 20 is actually 0.34. The tangent of 75 is about 3.73. So right here, about 3.73. So when I draw this, any triangle with a 75-degree angle and take the opposite side divided by the adjacent side, I'll get about 3.75. Tangent of 15 should be the reciprocal of that, so that's going to be approximately 0.27. If I were to figure out what is the sine of 75, again, just on a calculator, I get about 0.97, which is the same thing as the cosine of 15, because the opposite side of one is the adjacent side of the other. And the sine of 15 is about 0.26, which means that the cosine of 70, oops, I said 6, but I wrote 8, it is 6, which means that the cosine of 75 is also about 0.26. So no matter which right triangle you draw, if it has a 75-degree angle and a 15-degree angle, these are going to be the ratios of the sides, no matter how big or how small you have drawn them.